So today we're going to have a great presentation from Suresh Venkatesh from Princeton University. He's going to talk about integrated chip-scale solutions for electromagnetic synthesis and control for applications in communication, sensing, and imaging systems. Before we go to the talk, let me just introduce our Santa Clara Valley chapter. I'm the chair, George is vice chair, she is secretary. Haiming is also in this meeting. He's actually treasurer. Imran, who has been with us for quite some time, and he is webmaster and the e-notice he manages all the e-notices that go to the IEEE. Then we have few industry liaisons, Jonathan from Qualcomm, which is the same as my company, and then Robert was from Renesas, my old one, and then Dr. YK Chen from Alibaba. We also maintain a Facebook page, so I would, if you want to see any event, you can subscribe or you can like this page. And then we have this IEEE website, the CASS webs, our own SCV, Santa Clara Valley chapters website. We put usually all our topics. If you have any of you want to be volunteer, please do help us out. We obviously have a lot of things going on. And so 1 second, a couple of new people have come in. Let me admit all. Okay, and so, and then we post, actually last couple of posts I have not put on the IEEE TV, but we're in a mix of posting on IEEE TV or YouTube. It seems YouTube has become a very common medium, so we can post on YouTube as well. But we're recording this video. Also, we have just want to remind you guys of the future Circuit Systems events that's happening. So one is the ISCAS, that is the flagship event for the Circuit Systems Society. It's happening in May 22nd. Then the Midwest Symposium on Circuit Systems, which is the CASS flagship society for the region 6, I think this side of the region, like North America. So they're also having some fully virtual. Last time I mentioned about they had this deadlines, but now I think very soon, if you're a reviewer, a lot of people are joining. Okay, and then wait again. I think we started a little early. A lot of people are joining in. And so our also next event is it's actually a part of the Industrial DLP, Distinguished Lecture Program of the CASS. We have Dr. Ishwaran from TI. He's going to talk about the fault tolerant smart drivers for automotive systems, and this is also going to be a very interesting talk. I did not put it here because I am not. So this is obviously on Eventbrite. I asked every one of you to register for this event. Also, 2 more events are coming up. Again, one we are having is a DLP event. It's in June, first week of June, and before that we have an event. We have a talk on the from Slack, I believe, on the quantum systems and all the control systems over there. So with that, I'm going to stop share. And I'm going to give to, oh, wait a second. Oh, no, I have to sorry. I have to introduce 1 second. Just give me a second. Actually, a lot of people are still coming. So Suresh, just give 2 minutes more, okay?
Sure.
I don't want to miss the. Hussein's waiting. Okay. Yeah, we had a very high registration for this event. So this was a very popular event. So and since it's a little early for the Pacific time, I guess people are just getting out of work.
Okay.
So
yeah, it's fine. We can give like five more minutes.
Okay. I know it's a little bit late for you, so I apologize for that.
No,
but thank you. But thank you so much for taking time out.
Pleasure.
So. Okay, so let me start with the introduction. So today's lecture, as I said, it's from Dr. Suresh Venkatesh from Princeton University. He's going to talk about the integrated chip scale solutions, electromagnetic synthesis and control. Dr. Suresh Venkatesh received his MS degree in electrical and computer engineering from North Carolina State University in 2010, and his PhD in electrical and computer engineering from University of Utah in 2017 under the guidance of under the guidance of Professor David Shurik. His PhD dissertation received the ECE Outstanding Dissertation Award in 2016. He's currently a postdoctoral researcher at Integrated Microsystems Research Lab, Electrical and Computer Engineering Department at Princeton. He was also a research project assistant at Molecular Astronomy Laboratory, Raman Research Institute in Bangalore during 2007-2008. Where he worked on millimeter wave radio telescope. His research interests are in electromagnetics, metamaterials, antenna design, integrated circuits, computational imaging, and transformation optics design. He has authored, co-authored co-authored more than 35 journal and conference publications. He's an active IEEE MTTS volunteer and serving as IEEE MTTS YP Region 1 to 6 coordinator. He also serves as the committee member of Climate and Inclusion Committee at ECE Princeton University. So with that, I would like I'll stop sharing, and then I would like Suresh to start his talk.
Thank you, Amit. If you can you see my slides?
Yes.
Okay, thank you, Amit, for arranging this talk. It was always a pleasure. Today, I'll be, like Amit said, I'll be talking about electromagnetic synthesis and control, mainly looking into applications in communication, sensing, and imaging. So most of my work spans from microwave to terahertz regime. So let's dive in. So one of the things, as we step into the world of digital connectivity, communication and sensing platforms will play a very vital role. And not only that, different market trends are going to push these technologies in their very unique ways. Firstly, in terms of connected devices, as you might already know, the number of devices are growing exponentially, in fact, doubling every few years. Not only that, in fact, as these devices increase, the density of these devices also increases, which means that one needs to harness a larger part of the electromagnetic spectrum in order to accommodate all these devices. Next is, of course, in satellite internet, where people are enabling communications on the move kind of applications. This is basically pushed from SpaceX, OneWeb, Amazon, and so on. In fact, the number of satellite launches are, in fact, doubling every few years. Not only that, one important thing to note is that as these satellites come online, the user terminals that are going to be connected to these satellites are also going to increase, which means that we need to accommodate those devices as well. And lastly, in terms of connected cars and connected car solutions, number of sensors on board of these autonomous driving cars are going to increase, and these cars will start communicating with each other as well. So there is a blurring that will happen between communication and sensing platforms itself. So one needs to rethink about these platforms in terms of multifunctionality as well. So my research portfolio basically deals with design and development of such systems, looking into applications in communication, sensing, and imaging. So we basically make use of devices and antennas, develop them, and try to develop into systems. Of course, this involves involving electromagnetic co-design approach and mathematical tools and techniques that enable such designs. So like I said before, my work basically spans from microwave to terahertz regime. And at the outset, it's basically converting electromagnetic fields to bits and vice versa, converting bits to electromagnetic fields. So one of the things that I am interested is in developing massively reconfigurable electromagnetic platforms. And in order to do that, one needs to think about the design space itself. So we know there are electromagnetic handles that we can control in terms of spatial-temporal electromagnetic field attributes. But what do I mean by these electromagnetic field attributes becomes the first question. So any electromagnetic field can be characterized by its amplitude, phase, frequency, and polarization. So for example, if you had a good control over amplitude and phase, this could lead to programmable beamforming. If you had a good control over frequency, it could lead to programmable spectrum, programmable polarization, and so on. So we know all these handles exist, but how do you control these handles? That is where a co-design approach comes into play, and we need to bring in interdisciplinary fields like electromagnetic design, circuit design, novel materials, and computation techniques. When you do such a kind of a co-design approach, it will lead to multifunctionality and novel applications in communication, sensing, imaging, and also even computing as well. So the takeaway point is that a co-design approach could lead to multifunctionality. So, but what are the challenges in developing such an electromagnetic platform, especially at my millimeter wave and terahertz regime? So as we all know, there is a lot of push from 5G and 6G technologies, and there are newer bands that are opening up. As you can see, there is no one-stop solution across all of these bands, which means that we need to develop systems and devices across all of these bands that are opening up. Of course, at the lower frequency, there are good systems and devices, and we know how to control them and develop them. But as you can see at millimeter wave frequencies, there might be good devices. That doesn't mean there are good systems. So one needs to transition from devices to systems itself. At terahertz, that's another important electromagnetic spectrum band. There are no good devices itself. For example, CMOS and BiCMOS technologies are limited by their power generation capability, basically because of the device limitation itself in terms of FTF max itself. So shown here are some of the current trends in terms of generating powers from such CMOS and BiCMOS technology. But the important point is that there is a saving grace. The saving grace is that can we make use of the wavelength size itself? So especially given the size of the chips and the integrated chips and the wavelengths, especially at terahertz frequency, can we come up with systems and architecture that involve ICEM interactions? And can we develop novel systems based on such interactions? So that is the area that I'll be concentrating on in terms of developing such ICEM interactions that are possible to develop into systems and architectures. So let's look into terahertz systems. So conventionally, terahertz systems were basically inspired by optical counterparts. For example, they make use of a laser, which is a nonlinear crystal, and you can manipulate these terahertz beams with polarizers, waveguide bands, and so on. And again, you have a nonlinear crystal that detects these terahertz power. Like you can see from these pictures, these are bulky, not cost-effective, not scalable, and also sometimes require cryogenic operations in terms of operating them as well. So what if we envision systems that can enable chip-scale millimeter wave and terahertz systems? So what would they enable us to do? Of course, these chip-scale systems can be repeated and manufactured in large scale, which lead to low-cost, compact, and scalable systems. And also, they can operate at room temperature. But the important point is that one can think about packing large amount of radiating elements and large arrays on chips really close to the sources and sensors, which means that we can pack all these radiating elements on chip itself. And thanks to the wavelength scales involved at terahertz frequency, and this is possible. So I have basically divided my talk in these three electromagnetic spectrum bands. Basically, first I'll be talking about terahertz chip scale systems where we are enabling spatial and sub-wavelength control. for arbitrary EM synthesis. Next, I'll be talking about spatial time control, where we are trying to enable time-modulated arrays for physical layer security. This is some of the works at millimeter wave frequency. And lastly, very briefly, I'll be touching about spatial spectrum control in order to enable microwave computation imaging systems. So like you can see, I've divided my talk into 3 sub-bands from terahertz to microwave edge. So first, in terms of terahertz chip scale systems. So in this, I have 3 highlighted topics that I'll be very briefly talking about. First, in terms of terahertz metasurfaces that enable us to do a multifunctional programmable. So let's say we had a vision to develop a terahertz EM surface. What are its attributes, or what are the wish lists that we want to have? So we want to have independent amplitude and phase control so that we can do beamforming, high spatial speed modulation for spatial-light control. In fact, in general, if you had a really good control over the amplitude and phase at the near field, we could do any kind of arbitrary EM surface. But the question that we try to ask is, can I use integrated chips as Lego building blocks to manipulate these terahertz fields? In fact, that is where we try to ask the question, can such a IC-EM interaction, is it possible at terahertz? And the next question that we ask is, since we are interested in arbitrary EM synthesis and we need a really good control over the near field, can metasurfaces be an enabling technology on the chip scale platform? So a brief note on metasurfaces for people who don't know about metasurfaces and materials. These are basically engineered materials where we can control and manipulate electromagnetic fields. And these are basically periodic arrangements of subwavelence scatterers and unit cells where we can engineer electric permittivity, magnetic permeability, and so on through homogenization approach. These gained a lot of traction because they were able to generate large index gradients, negative refractive index, anisotropy, chirality, and so on. Shown here is one such application of these metasurfaces where they're trying to hide these undulations that you see on these surfaces. And by having these metasurfaces, this behaves as though this is a plane mirror. And that's why it's called as a carpet cloak. But let's do a simple thought experiment in terms of can we enable integrated chip EM interaction at terahertz fields using these metasurfaces. Let's say at 0.3 terahertz, the wavelength is about 1 mm. If we are talking about subwavelength structures, let's say the unit cell structure is about lambda by 10. One could pack about 10K unit cells in a centimeter area square. So that itself becomes an enticing approach in terms of taking such metasurfaces to electromagnetic chips. And this is possible to do at integrated chips as well. So of course, I'm not the first one trying to do a terahertz metasurface. Of course, there are existing technologies and demonstrations. Shown here is one such demonstration where they're trying to do amplitude and phase control through such split ring resonators where they control these gaps, capacitive gaps here. And by controlling these capacitive gaps, they can get amplitude control. By opening these capacitive gaps, they can get good phase control. And these are subwavelength control. And of course, there are also implementations at optical frequencies where they're trying to do flat lenses. This is one of the works from Capasso's group where they are trying to correct for chromatic aberrations in this particular case. But as you can see, these are meant to be passive structures without any kind of tunability. And they are very unifunctional. They're meant to do very specific tasks. Of course, there are kind of tunability that have been demonstrated, especially using heterogeneous integration methods like vanadium dioxide, 2D materials.
Hey, Suresh.
Yep.
Just 1 second. Can others please mute their mics, please? They're having a lot of. See if you. I don't know. I hear a lot of car noises and somebody's driving. Thank you. Or I can mute all, and then I think Suresh, you need to unmute yourself. Yeah. I unmuted you.
Can you hear me now?
Yeah.
Okay,
that's good.
So basically, these structures that people have demonstrated are passive, without any tunability once they are fabricated. So of course, some kind of tunability have been demonstrated using heterogeneous integration methods, like I said, in terms of vanadium dioxide, 2D materials like graphene, molybdenum disulfide, and so on. But they require external stimulation in terms of high voltages, heating, optical pumps, and so on. So such kind of an approach is not scalable. They're inefficient, power hungry, and so on. So the question that we ask is, can I dynamically create these subwavelence scatterers on the fly, and preferably on a monolithic integrated platform? The answer is yes. What if you took transistors as switches, make them as switches, make them behave as switches, and try to control these capacitive gaps such that it emulates these rotation of these flickering resonators shown here, and try to control amplitude through such switch configuration. And by opening multiple switches, we can control phase as well. But the problem is that if you took a 65 nanometer bare device and try to ask what is its on-off switching ratio at 0.3 terahertz, it's terrible. It's a factor of 2, which means that these switches are terrible at 0.3 terahertz. So that's where electromagnetic circuit co-design approaches come into play. In fact, we can enhance these switching ratio by having these micro loop structures around these transistors, wherein we resonate out the device capacitance of these switches. By doing so, we can get an enhancement of 12.5 in terms of the switching ratio. And now we can think about dynamically tunable subwavelence scatterers at 0.3 terahertz. So, and that is how EM and circuit co-design approaches come into play. Shown here are some of the simulations in terms of enabling such amplitude and phase control. Shown here are very few switch settings, some highlighted switch settings. For example, having a switch open at this particular gap, we can have a good resonance at 0.3 terahertz. By having a switch that is orthogonal compared to this one, the S parameters and the field configuration drastically change. And the same thing happens when you have all the switches open or all the switches closed. So now that we have all these subwavelence scatterers, now we can think about creating a big transmissive tile structure with these subwavelence scatterers trying to manipulate the near field, thereby engineering the fabric. So one where we can come in with a terahertz beam from the back end and illuminate this transmissive tile structure, manipulate the near field, and try to engineer our fabric. So that's our aim, and that's what we want to do. So in order to do that, we fabricated these subwavelence scatterers in a 12 by 12 array format on a CMOS industry standard CMOS platform, and we control each of these transistor switches at these capacitive gaps through a high-speed digital backend. And this is one particular unit cell, and this particular unit cell operates at 0.3 terahertz, and it's about lambda by 7 in terms of its size. Like I said before, these switches are digitally programmable, and in fact, we have an on-chip high-speed digital backend to control all of these switches. And this whole thing was realized on a 65 nanometer CMOS technology. So here are some of the measurements when we have these different switch controls, where we are trying to rotate these switching gaps. We can have really good amplitude control. In this case, particularly, we can have an amplitude variation of 25 dB, wherein we keep the phase more or less constant. And in the other case, where we try to open these switch gaps, we can control the phase while keeping the amplitude more or less constant. And this particular structure that we fabricated has an 8-fold symmetry, which means that you have 84 unique combinations that you can create in terms of on-off switching. And based on that, we can have an amplitude variation of 25 dB and a phase variation of about 260 degrees. So now we can think about these subwavelence scatterers to manipulate the near field, since we have good amplitude and phase control, and try to project out far field patterns. Not only that, since these are chips, now we can tile these chips in our 2x2 format. In fact, we have 576 independently controllable unit cells in this particular case. And once you have a large surface, the obvious thing to do is to create phase gradient across this surface and try to do beamforming. And that is exactly what we show here, where we are able to do beamforming of plus or minus 30 degrees. And the important thing to note is that this is each of these chips here consume about just 240 microwatts, which means that this is near zero DC power consumption of trying to do terahertz beamforming. And it's a mixer-free architecture of doing terahertz beamforming. So that is very enticing in terms of taking such approaches. Another thing is, since we have really good near field control, we can project out different structures in the far field. In this particular case, we project out P and U corresponding for Princeton University. Shown on the left is the simulation, and shown on the right are the near field and the Fresnel zone measured patterns. Like I said before, since we have high-speed digital backend control, we can control these surface at extremely high-speed rates. In fact, we can program and switch these beams from all the way from off to on, and get an amplitude depth modulation of 25 dB at up to 5 gigahertz of clock switching speed. So that, what we can now imagine is that let's say we come in with a terahertz beam, we can switch these terahertz beams at extremely high-speed rates, which means that we can put in on-off keying in order to communicate between such surfaces now. So the surface itself can start communicating data as well. So that is, again, another approach that such platforms can do. So what I explained before was in terms of the terahertz metasurfaces, but I've also worked on microwave regime of metasurfaces. Shown here are some of my previous works where we looked into focal plane arrays using metasurfaces. On the top plane are these electrical coupled resonators, and on the back plane are these discrete circuit elements that control each of these pixels. Of course, now there are companies that are trying to do electronically scanned antennas using metamaterials as well. And again, we can also do microwave regime of metasurfaces using thin film transistor switches. Again, in this case, these are TFT switches that are in-house fabricated at Princeton, and this was one of our works in IEEE 20. So this was an brief outlook on how metasurfaces can enable such different kinds of EM platforms in terms of multifunctionality. Next, I'll be talking about my work on enabling terahertz localization through what we call a terahertz Prism approach or spectrum to space mapping approach. So let's say, let's say we are interested in localizing wireless beams, wireless nodes. One way to do that is, of course, you send out a broad beam and scan the beam in space. By having a broad beam, we can wherever the signal to noise ratio peaks, that's where our wireless node is, and that's how you localize the wireless. So depending upon the broadness of the beam, you'd be limited in terms of the signal to noise ratio and accuracy. But however, if you had a really broad beam, your rate at which you can localize wireless nodes would be relatively faster. One way to improve the accuracy is through making the beams narrower. But in this case, you'll have to scan more number of angles, which means that this process will be slower. Of course, an intermediate approach would be to have multiple beams that goes through different space. And by having such a thing, you would get an intermediate in terms of signal to noise ratio and accuracy, but this would be relatively faster. Nevertheless, all these three approaches are iterative in their process. So the question that we ask is, can we do, or can we enable localization of wireless nodes in a single shot fashion? That is where a Prism kind of an approach comes into play, wherein we are trying to do spectrum to space mapping. Let's say you had a source that would broadcast different frequencies to different locations, and these wireless nodes would receive different parts of the spectrum depending on their location. And by the spectrum that they receive, they can immediately localize themselves simultaneously in a single shot fashion. So now the question becomes, how do you enable such a spectrum to space mapping in order to localize these multiple wireless nodes in a single shot fashion? And that is where Prism kind of an approach or Prism kind of a radiator comes into play. A Prism basically does the similar thing. It takes in white light, broadband spectrum, and splits out different frequencies to different locations. So how do you enable such a spectrum to space mapping? So in order to do spectrum to space mapping, we need to develop antennas that do that. In this particular case, we can make use of frequency dispersive antennas. And these dispersive relationships can be controlled as well. So in this particular case, we have these leaky wave antennas, wherein we control the dispersion relationship of these leaky wave antennas through these metallic caps and also the SIW waveguide in which this wave is propagated. So by having such leaky wave antennas, let's say you came in with the different frequencies, you excite these antennas at different frequencies, the lower frequency would end up in the broadside region, and the higher frequency would end up in the end fire region. So this would cover one end of spectrum to space mapping, at least one half hemisphere of the spectrum to space mapping. By having a similar antenna that is excited from the other end, you can cover other half of the hemisphere, and now you can enable two of these antennas that will cover the full 1D hemisphere. So shown here is one such simulation at 380 gigahertz of this Leaky wave antenna. When you excite these antennas from one end, most of the energy dies down, which means that these energies are getting leaked out from these slots that we have here. And that's how we can control these beams at different frequencies. Shown here is again the implementation. This was implemented at using 65 nanometer CMOS technology. This particular antenna, this particular chip has two antennas, and this can behave as either a transmitter or a receiver, or also as a transreceiver mode. And this whole chip operates between 360 to 400 gigahertz. Here are some of the system specs that we have in terms of the transmitter and the receiver chain, but I wouldn't go into too much details here. But what the important thing that I want to highlight here is that by exciting the antenna from one end, these are the measured beam patterns. The low frequency ends up in the broadside region, that is 365 gigahertz, and the high frequency, that is 395 gigahertz, ends up in the end fire region. By having another antenna that is excited from the right-hand side, we get these dotted lines that is covering the other half of the hemisphere. And now we can think about enabling spectrum to space mapping. So once you have such a spectrum to space mapping, the other question is, how do you enable localization? So we create a big calibration matrix based on the spectrums that we receive at different locations. And this calibration matrix acts as a basis vector to do localization. For example, let's say we measured a spectrum from an unknown location, then we can try to correlate with the known calibration matrix that we have a priori measured, and then try to estimate the theta at which this particular spectrum is at. And by doing so, we can localize multiple wireless nodes simultaneously. What I explained was 1D localization. Of course, we can also do 2D localization by strategically placing two of these chips in an orthogonal fashion. And by having two of these chips, we were able to show a localization error of just less than 2 degrees in both theta and phi direction. Of course, all of these measurements depend upon resolution bandwidth and the measurement time. And we discuss all of these in detail in the paper. Lastly, in terms of my terahertz chip scale systems, I would be talking about my CMOS terahertz phase array, where we are trying to generate terahertz power and also do beamforming with these generated power. Like I said before, generating terahertz power from CMOS devices, which are FTF max limited, is extremely hard. So which means that one needs to explore or exploit the nonlinear behavior of these transistors to generate power. And which means that we need to make use of harmonic oscillators and so on to generate terahertz power from CMOS and BiCMOS technology. But the problem becomes that if you had different harmonic oscillators, how do you generate a coherent power? Because each of them would have process voltage, temperature variations, and you would not get a coherent power. One way to get coherent power is to actively or passively couple these sources, multiple sources. But of course, we can pack a large number of sources in a given area. Thanks to digital electronics, we know how to pack transistors. So we can pack large number of sources, which are harmonic oscillators, but we need to somehow make sure that they are locked. Once you have a large number of sources, the other thing that we want to try is, can we create a phase gradient across these sources so that we can enable beamforming? So that becomes the next challenge. And lastly, the challenge is once you have generated the power, you want to optimally load your final power generating states so that you can radiate all this power and then spatially combine this power. So transmission lines based combining at these frequencies is extremely lossy. So you want to radiate out this power and try to spatially combine this power. So let's see how we try to solve all these three challenges. Firstly, let's say we had two coupled oscillators that are oscillating at the design frequency. One way to couple them is to have such transmission lines that are connected between these two oscillators. So one way to think about is that some part of the oscillator current would get injected to the other oscillator, and that's how coupling mechanism is established. But as you can see, the inductor in the LC resonator tank can itself be thought about as a coupling network, and that is exactly what we do. And we make sure that all of the currents from oscillator 1 becomes the injection current to the other oscillator. And by judiciously choosing this resistor, we may ensure that no current flows to the VDD part of it, which means that we can, in fact, we can show through Adler's equation that the locking mechanism is extremely robust when you have the oscillator current become equal to the injection current. And doing so, we can establish highly locked sources through such mechanism. So that's how we try to solve first the problem of locking these sources. So once you have these highly locked sources at lower frequency, in this particular case 69 gigahertz, then we try to create these multiplier chains. In this case, a doubler, injection transistor, which acts as a frequency reference to a free-running 3-stage ring oscillator. And this 3-stage ring oscillator generates 416 gigahertz, where we optimally load this particular stage with a patch antenna. So that's how we try to solve the optimal loading problem as well. And not only that, each of these negative Jim cores or these cross-coupled oscillators have varactor diodes in them, varactor capacitors in them, which means that we can create small phase gradients across these highly locked sources. And thanks to the multiplier chain, this small phase gradient multiply by a factor of 6, which means that now we can also enable beamforming as well. And that is how we try to solve both optimal loading in terms of spatially combining this power generated and also trying to do beamforming as well. Not only that, our approach is also scalable. Now we can think about creating n by n array of these oscillators. And by having such, in this particular case, each of these negative Jim cores have a doubler, injection transistor, and a 3-stage ring oscillator, and then a patch antenna. And these patch antennas are lambda by 2 spaced apart as well. And like I said before, each of these negative GM core cells have varactors in them. We show that by varying these varactors across these networks, we were not able to see any kind of beating, which means that we have extremely robust locking mechanism as well across this whole array. In fact, this whole array behaves as a single oscillator in this case. And that is exactly what we implemented, and shown here are these structures that I mentioned previously. And we were able to generate a peak EARP of 14 dBm. And the important point to note is that this EARP is in a lensless approach, and which means that this is the power radiator and the gain of the antenna rates. And shown here are some of the beamforming we were able to achieve. We were able to do plus or minus 30-degree beam steering, both in 1D and 2D as well. So that was mostly my work in terms of enabling chip scale systems at terahertz frequencies. Next, let's look into spatial time control, where we are trying to do physical layer security for time modulated arrays. So firstly, why is physical layer security or cyber physical security important? As I showed before, the number of active devices are increasing, and so is the attacks on such devices, which means that one needs to rethink about security itself. In most of the cases, in a wireless network layer, security is implemented on the topmost layer, which is the application layer through HTTP protocol and so on, and which means that the bottom layers are exposed towards attack. And the most exposed layer is the physical layer, where we can attack these systems through eavesdropping, jamming, and so on. So that's where the protection has to start. We're in a critical system, and that is why a physical layer security is extremely critical. So let's think about how one can implement or how one can analyze physical layer security. Let's say there is an intended transmitter, in this particular case, Alice, trying to send data to an intended receiver, that is Bob. So Alice would try to find a very good channel, high gain channel, and try to send data towards Bob, which means that Bob would receive high signal to noise ratio signal, which means that this data is demodulated or decoded. But let's say in the same environment, there is an eavesdropper trying to look into this data that is being sent out to the intended receiver. Somehow Alice has to send the same data, but through a lower gain channel, assuming that this data would be not decoded because this data would have lower signal to noise ratio. But what Alice doesn't know is that what is the sensitivity on the receiver part of the eavesdropper. If the eavesdropper had really good sensitive receiver, even though you might receive low signal to noise ratio, this data may be demodulated as well. So that is what such a lower gain approach or lower channel approach may not work in terms of physical areas. But unfortunately, or fortunately, physical phased arrays do exactly the same. For example, all the temporal data that are generated are fed to all of these antennas simultaneously. And of course, you would apply a particular kind of phase gradient across these arrays and then try to create these main lobes. And that is where your intended receiver is going to stay, and you receive a high signal to noise ratio signal, and this data can be demodulated. But if, let's say, an eavesdropper is sitting at the side lobe level, same data is still received, but with a lower power. But depending upon the sensitivity on eavesdropper, this data can still be demodulated. So such kind of a power approach may not work in terms of enabling physical layers. So how do you think about physical area security in terms of robust systems? So shown here is, again, for a phased array, as you can see at different angles, it is still a QPSK, just a scaled and a rotated version. In fact, you can plot the bit error rate as a function of angle and show that the bit error rate for a 4-element array is really low at the side lobe level, which means that if you are sitting at the side lobe level, this data can still be demodulated. So the question that we ask is, let's rethink about the Weiner's wiretap channel in terms of analyzing physical layers. Suppose Alice can send data towards eavesdropper in a time-varying channel while keeping the link between the intended transmitter and the receiver intact. How would that enable to achieve physical layer security? Since this is a time-varying channel in this particular direction, you would intentionally introduce spectrum aliasing in this particular direction, which means that now this spectrum is all garbled up. And that is how we can try to think about physical layer security in this particular case. So let's see how to enable such a kind of an intentional garbling of the spectrum at a particular direction through intentional spectrum aliasing. That is where a time modulated approach comes into play. In this particular case, let's say you have different symbols, symbol 1 to symbol n. For example, at time instant 1, you would send symbol 1 to antenna 1, symbol 2 to antenna 2 at time instant 2, symbol 3 to antenna 3 at time instant 3, and so on. As you can see, at the broad side, all of these symbols would align in time, which means that the intended receiver, that is Bob, would get a really good spectrum, and also the constellation is very well preserved. At any other angle, all these symbols get misaligned in time. And that is where you get an alias spectrum, and these constellations are completely garbled up. And that is how you can achieve physical layer security through such time modulation approaches. But the only thing to remember is that the switching frequency, as long as it's less than the data bandwidth, such kind of an approach is still possible. So this is the only condition that you need to meet. So let's look at the constellation. So it would begin with a good QPSK at 0 degrees, and as you go to higher and higher angles, there would be a constellation splitting that would happen, which means that this data is not recoverable. In fact, you can now start comparing with a phased array and a space-time modulated array. And as you can see, the space-time modulated array is plotted in blue, and the phased array is plotted in red. And at, let's say, at minus 60 degrees, where the side lobe location for a 4-element array is, you will see an immediate jump in the bit array, which means that you can think about ensuring security if there's a eavesdropper sitting at the side lobe location. In fact, this kind of a security also enables physical layer security without need for cryptographic key exchanges, which is an additional feature of this kind of an approach. Again, this whole idea was implemented on a 65 nanometer CMOS process, and this particular chip operates at 71 to 76 gigahertz. This particular chip has 2 independent transmitter chains, and each of the transmitter chains have a mixer and a 3-stage PA, and the second and the third stage of the power amplifier are controlled through these switches, and that is where we input our external time modulation signals. And once the power is generated out, we wire bond this to an off-chip series fed patch antenna where we radiate out this power. Shown here is a 2-element array implementation with 2 such antennas. And we are also able to show a scalable architecture in terms of making use of 2 such chips and trying to develop a 4-element array as well. So let's look at some of the measurements. So without any kind of a time modulation, this would behave as a simple phased array. And as you can see, at 0 degrees, you would receive a good spectrum, and the constellation is very well preserved. And at 60 degrees, you would still receive the spectrum, but with a lower signal to noise ratio. But this data can still be demodulated. It still looks like a good QPSK. But when you turn on your time modulation, you still receive a good spectrum at 0 degrees, which means that this data can be demodulated. At any other angle, as you can see here, at 60 degrees, there's a spectrum aliasing that happens, and you can see the broadening of the spectrum, and the constellation is completely garbled up. In fact, we show these constellations as a function of angle. As you can see, as you move away from 0 degrees, in this particular case, the constellation is getting garbled in space as well. So now, what I explained was periodic switching. So you don't have to necessarily switch your antennas periodically in time. Now you can think about chirping or randomly switching your frequencies, frequency of switching of these antennas. In this particular case, we chirp our frequency of switching as well. And doing so, we can garble our spectrum even drastically. In fact, we can now think about RF jamming the eavesdropper as well. So those are some of the things that we are exploring as well. What I explained was in terms of how to mitigate an attack. But one of the questions that we are also asking is, how good is our system in terms of the attack itself? So can we attack our time modulated array itself? So as you might imagine, different eavesdroppers would receive some part of the data, even though it might be alias. As long as you have many eavesdroppers that would collude among themselves, you could still try to ask what was the data that was being sent out. So in fact, we can write it in a mathematical form. In this particular case, if y is the number of eavesdroppers that you have and the signal strengths or the signals that these eavesdroppers would receive, and x is the excitation or the data that is being sent out, and h is the transfer matrix or the channel matrix that relates the excitation in the receiver. So by knowing the channel matrix, suppose you know these channel matrices, you can invert this channel matrix and try to ask the question, what was the excitation or the data that was being sent out, assuming that all of these eavesdroppers would collude on themselves. But the thing is, determining the channel matrix across the space is extremely tough, and any errors on the channel matrix would immediately transfer as errors on your data stream that you are trying to reconstruct. So that is one of the things such a channel immersion-based approach doesn't allow us to do in terms of determining the channel matrix across the whole space. So another thing is, let's say you knew some of the pilot bits that are being sent out, and you can analyze these constellation mapping or these constellation dynamics that are happening across the space. By having a neural network, you can train these constellation dynamics and try to ask the question, what was the data that was being sent out if you knew some of the pilot bits. In fact, we compare how these channel immersion-based attacks compare with neural network-based attacks. In fact, to achieve a bit error rate of 5%, you need about 10 eavesdroppers that needs to collude among themselves, and that is how we can show how robust is our system in terms of eavesdroppers, colluding eavesdroppers. So that was a brief outlook on how we can enable spatial temporal modulation to enable physical layer security. And lastly, I'll be very briefly touching about spatial spectrum control, where we are trying to enable a microwave computational imaging approaches to origami-based platforms. One of the things that we are interested is in developing sparse multi-static arrays, wherein these static arrays would have both transmitters and receivers. And without doing any kind of a NICU sampling across the space, we still want to reconstruct or image a standoff target. So first question is that even possible? And what are the things or what are the attributes that these transceiver planes need to have in order to reconstruct the scene that is the distance away? So in order to do that, let's say you had a bunch of transmitters that would send a diverse beam and try to emulate the external or the standoff target based on the scattered or the backscattered signal that are coming back to the aperture. One can receive all these backscattered signals and then ask a question, what was the target or what was the scene that led to my measurements here. So that is again where inverse-based imaging and computational imaging comes into play. And in order to do such kind of approach, you need to have extremely good orthogonal measurements because you have to invert a matrix in order to reconstruct the scene. And that is where we need to enable frequency and spatial diversity in terms of these multistatic transreceiver apertures. So in this particular case, we made use of origami and metasurfaces to have both frequency and spatial diversity. Basically, the spatial diversity is provided by these shape morphing origami platforms, and the frequency diversity is provided by these origamis or these metasurface style radiators that are operating from 17 to 26 gigahertz. And in this particular case, we had about 22 metasurface antenna tiles. Each of them could be either transmitters or receivers. For example, one of these antennas would be transmitting the power to the standoff target, and the rest of the antennas would receive the backscattered signal. And then a next antenna would turn into a transmitter, and the remaining antennas would act as a receiver. And once you have all these backscattered signals that you have measured, you ask a question as to what was the target that led to all of these measurements. And that is where we have to invert, again, a channel matrix in order to reconstruct these scenes. A brief note on these origami tiles. These are, like I said, shape morphing apertures, where it can take different shapes from rectangular to cylinder to convex and concave shapes. And the question that we ask is, what is the shape that I need to have in order to achieve a particular kind of imaging modality? And these imaging modalities can be field of view, resolution, signal to noise ratio, specularity, and so on. So in fact, we can ask the question, what is the structure I need to have in order to achieve a particular kind of imaging or a better imaging of a target? And those are the questions that we are indeed asking as well. So again, a brief note on the metasurface style itself. And these are frequency diverse radiating elements, which means that the far field patterns drastically change across the bandwidth. In this particular case, the 17 gigahertz far field pattern is completely different from 22 gigahertz, and the 22 gigahertz is again completely different from 27 gigahertz. In fact, we can plot the correlation matrix of these far field patterns, and as you can see, it's a block diagonal matrix, which means that the far field patterns have very few correlations across the frequency domain. Shown here are some of the imaging that we were able to show. In this particular case, we have these origami structures shown here, and these are these metallic strips that are 1 meter away from these apertures that we are trying to reconstruct. So in this particular case, we have two shape morphing structures. One is the stretched case where the aperture becomes bigger, and the unstretched case where we squeeze the origami structure. So of course, when you have a bigger aperture, you receive high spatial K vectors, and you can resolve better finer targets. In this case, we were able to resolve up to 1 centimeter. And of course, when you squeeze your origami, you lose out on your resolution. But most of your measurements would rely on low spatial K vectors, which means that they are, in general, high signal to noise ratio measurements. So your image reconstructions would be better as compared to your stretched origami case, wherein you are trying to measure high spatial K vectors, which are some more or less low in terms of their signal to noise ratio. So that's how we can trade off between signal to noise ratio and resolution in this particular case. Not only that, we can also curve our origami. In this particular case, when we curve our origami, we can reconstruct these complicated 3D targets, and also we can compare with a flat origami that we have this particular case. So since this particular 3D scattering target is extremely specular, we need to eliminate these targets very effectively so that we are not limited by the specular reflections. For example, when you eliminate with flat origami, most of your measurements that you are going to make are highly specular, which means that your reconstructions are inundated by these specular measurements, and you lose out on these intricate details. But when you curve your origami, you eliminate your structure very effectively. In fact, you also increase your field of view, which means that you can in fact, try to know all these intricate details of these standoff targets. And that's how we can compare and try to trade off between different kinds of shape morphing architectures to the imaging modality. So finally, I'd like to conclude by saying that some of my research is going to impact satellite internet, IoT devices, Going forward, it will also impact autonomous cars, drones, and so on. In fact, Department of Homeland Security is looking into revamping the airport security scanners in terms of curb-to-gate screening methodologies. And at the outset, asking even the fundamental limits of computing and imaging limits as well. So at the core of all of this lies reconfigurable, intelligent electromagnetic platforms that spans across the electromagnetic spectrum. So I'd like to thank some of my lab mates and my group members at IMRL, Princeton University, and also our funding agencies. And with that, I'm happy to take any questions and have a discussion.
Yes, thank you, Suresh. That was a great talk, I think. You covered so many things. It's amazing to see that. Do we have any questions? I should also let everybody know that it's late for Suresh. Suresh is based in East Coast, so let's keep the questions to few.
Probably you might want to unmute them, I suppose.
Oh, sure. I think they can mute themselves, but okay, I can do that.
So great works, Suresh. Congratulations on these publications. I have this question, like how bad is the attenuation, atmospheric attenuation in the terahertz regime? And
yeah, so that's a good question. So, for example, there are these molecular absorption lines which attenuates your signals drastically. So that's a problem. But there are bands wherein the attenuations are not that high because of these absorption lines. But even the FCC opens up these bands strategically where there are no absorption lines. So that is where you need to operate your devices and systems. But nevertheless, that being said, we are still limited in a lab setting, which means that we are not that much affected by the attenuation and the absorption lines one might think of. So,
I have a question.
Sure.
How well does this work, let's say outside, inside a forest or, in a place with lots of objects?
That's a good question. So, I mean, we know that satellites and drones can do imaging. But nevertheless, most of my work has been in controlled environment in a laboratory setting. But yeah, pushing systems towards such kind of domain and environment is itself a challenge itself, right? So that is something that we need to explore. That is not something that I'm currently exploring, but yeah.
And
it is definitely challenging, yeah.
Yeah, I have a related question. So can people block this?
Sorry?
Can they
which particular work are you talking about? The time modulated array, the security?
Yeah.
So, I mean, can someone jam our system? Yes. I mean, you could. In our particular case, we are a transmitter. So, I mean, we are not a receiver. There are also time modulated receivers that one could think of. In that particular case, you could try to jam with, extreme high powers. But that's not the thing that we are trying to demonstrate or trying to talk about here. So we are talking about how to send data in a very specific direction so that nobody else can receive. For example, if you had a simple phased array, the same data is being sent out at the side lobe level. So if you had a good sensitive receiver, you can still receive that signal. But how do I send data in a very specific direction so that nobody else can receive is the question. I don't know if I answered your question, but.
Well, I was thinking more of like if there's someone who's trying to both eavesdrop and interfere with you such that kind of mask your results so that you thought you're getting it from someone or from some direction, but actually they changed it. So it's not just blocking, but also interfering or modifying your feedback.
True. So in a time modulator array, you're trying to induce aliasing in a specific direction. So if you are a receiver, from a receiver perspective, right? So if you are a good intended receiver, you would still receive your spectrum from the intended transmitter. But of course, some other person can try to jam the intended receiver, right? So that is not something that is under my control, though. I'm trying to send data in a specific direction, assuming that there is no other jammer that is trying to jam my intended receiver. That's the assumption here. Yeah.
Okay. Thank you.
Okay. Any more questions?
So in your lab environment, what's the range have you measured for this to be effective?
For the millimeter wave, we can go up to a few meters, but the terahertz is like mm or 2 mm chip, so it's like in centimeter scales. Yeah.
Thank you.
So Suresh, for the EM manipulation, you were using switches, right? That you showed, I think. Yeah. So, and then you obviously showed us some C on, C off ratios, and then how, but you still did on 65 nanometer technology, I think. So my question to you is, when you show all this, do you think the switches linearity, some of the frequencies that it comes out of those switches, do you have to think about those as well? Those harmonics coming out of the switches, that kind of. Go ahead. I mean,
Yeah. So the switch itself is not trying to switch at terahertz. So the switch is switching at lower frequency. So, but it's giving a impedance that I need to have at terahertz frequency. So as long as I get a good impedance ratio at terahertz frequency, that is what I care about. I'm not trying to switch the switch at terahertz frequency.
No, that I understand, but the switch itself probably has, I mean, the impedance is all over the place, right? So, go ahead. Yeah, sorry.
The thing is that these structures are extremely resonant. So we are only trying to, we may ensure this whole structure resonates at one particular frequency. We're not trying to make sure this is broadband or anything of that kind. So in this particular case, it's only 8.3 terabits. Yeah. Sorry, go ahead. You had a question.
No, I was just asking in terms of if you look, because I think you're controlling these impedances, RDS or whatever of these guys, right?
Yeah.
Correct?
Yeah.
So this RDS is quite a non-linear thing, correct?
Correct. Yeah.
Correct. So, I mean, at this frequency, I don't know if it's something's happening. I'm just kind of, being inquisitive about that effect that you may see in this frequency, because I've never done this kind of high frequency. So
so I mean, as long as that impedance profile doesn't affect my 0.3 terahertz in this particular case, I'm good. I'm good.
Okay.
Of course, there would be a different kind of a response depending upon your structure and your transistor at different frequency, but that is not the place where my electromagnetic subwavelength unit cell is resonating. So I don't care so much about that particular case, but you're right. Of course, there would be a different kind of an impedance profile depending upon your micro-inductive loops and your transistors and so on. Yeah. But that I don't care about, because that is not the frequency that I'm operating in.
Okay.
As long as I get a good impedance, on and off impedance at that particular frequency, I'm good.
Okay.
And that is what we try to engineer.
Okay. Sounds good. Thank you.
I have another question. For your origami, you talk about stretch on stretch and dome and subtle shape, all that. How much software massaging do you do of your data? Because if there's a problem with calibration or part of it is not working, are you able to work around that, or does that create artifacts in your data?
Yeah, that's a really good question. So, of course, so in this particular case, we need to know something called as the image transfer matrix. So how do you construct an image transfer matrix? You let me try to, I think I had some backup slides. So I don't know if you can see this particular case. So you do a near field scan of your antennas, try to get the amplitude and the phase profile of each of the antennas, right, across the frequency, and then try to create this big matrix that takes you from your measurements that you make and the scattering voxels that you have. So you have this 2D matrix across all these frequencies. And once you have a near field scan, you can also far field propagate them. So then you try to invert this matrix. So all of your measurements relies on these transfer matrix and these measurements that you make in terms of trying to create this image transfer matrix. So your first 101 is in a inverse based or a computation based imaging is that how do you construct these effectively these transfer matrices? And that is where most of your errors come from. Of course, the other errors come from trying to know where your structure is and how well you have rotated and how well you have determined that structure. So in order to do that, we use Kinect sensors, wherein we try to map these antennas, how they're oriented. And based on the orientation, we also rotate our fields accordingly, and then try to construct these image transfer matrices based on the rotations of your structure or your placement of your antennas and so on. So constructing that image transfer matrix itself is a task, and errors on that would also propagate as errors on your image reconstruction. So that's a really good question. So yeah, you're right. So one needs to ensure that a really good calibration happens in terms of constructing these image transfer matrices. But this has to be done once though. You don't have to keep on repeating them. So as long as you do it once, you can keep on using the same image transfer matrix for different kinds of targets. You don't have to redo these measurements.
Well, also another question, is this affected by like weather conditions?
Yes.
So
yeah.
and temperature and all?
Yeah, let's say you had a turbid medium and I measured my image transfer matrix in vacuum or air. So that wouldn't work. So that turbid medium itself is a scattering channel. So you need to take into account those as well. And there are methods wherein people indeed take different kinds of turbid medium and try to do such methods as computation methods, where you can correct for as long as you a priori know what is the medium and what is the channel, you can try to correct for those conditions as well.
Thank you.
So Suresh, in terms of the silicon process that you use for all these technologies, is it all CMOS stuff that I'm guessing that you did?
Yeah.
All right. So
yeah.
do you think that there is just for the information's sake, would you rather kind of choose other processes as well, something else that could make things more easy?
Yeah, anything that gives you better FTF max, that's always a choice to go, right? But there are, again, challenges when you go to different processes. Maybe they are not mature enough, but 65 nanometer is like a workhorse, right? So you'd always want to stick to that, and it's also low cost. So that's one of the reasons why we try to do 65 nanometer.
Sure, but
we also do other processes as well.
Yes, but then you also want enough power, right?
True, correct, yeah. So there's a trade-off, yeah.
Okay. Okay, I think does anybody else has any more question, because it's quite late for Suresh, so I think we should let him go.
Yeah, I mean, you can always find me on email. And
Sure. Yeah. So with that, let's conclude this talk. Thank you so much, Suresh.
Thank you.
I think it was a great talk. Covered a lot of things, and it was quite amazing. So with that, I'd like to thank you again for coming, giving us a talk. And hopefully next year when things get better, you can come over and give us a talk in person.
Yes, definitely. Yeah. Thanks, Amit.
That'll be super great.
Yeah.
All
Thanks,
right.
Amit. Thanks.
Sure.
Thanks a lot. Bye-bye.
All right, then.
Take care.
Then thank you, everyone. Take care. Bye-bye. Bye.
Bye-bye.